This is part two of our series on comparative statistical tests. In the prior section, we talked mostly about different levels of measurement, and the reason why we need to know those, as you'll see in this section, is it will determine which of these tests we use. Um, the first thing is, again, by way of review, is to remember that each of our different types of questions we ask lead to different tests. So we have descriptive tests, we have correlation tests. We're studying the comparison tests in this session. And we also have predictions and issues that are related to epidemiology. So the type of question we ask leads to that type of study, that type of analysis using a different statistical test with our outcome. One particular type of research question that we see in the comparatives is a format known as the PICO question, P-I-C-O-T. When we use this type of question, we can only answer this with a comparative test. We often use this with evidence-based practice implementation, where we're comparing an old way of doing things with the new way. It's an acronym, and it's meant that we write this question in that order. And these are what the elements and the letters stand for. P is for population or problem of interest. I is for a new intervention or implementation. C is a comparison group, often the older way of doing things. O is the outcome, and it's important to realize it is outcome, not outcomes. It's singular, just one outcome. We might also consider that to be our dependent variable. And time is for the element, or T is for time, the element of time, the duration of the study. As an example, consider this PICO question. And you often see PICO questions written like this, where the element, the letter, is either before or after that in the question. So here we have our P is an obese patient, does, and our I is the implementation of the keto diet. C, as compared to having a regular diet. O, result in greater weight loss. T, over a 6-month period of time. In this type of question, by default, the I and the C are actually two comparison groups with one IV. We don't actually see the IV typically stated as an independent variable to PICO. Instead, we get its two comparison groups. And if we look at these two groups, we can say that they're both types of diet. So here our independent variable might actually be the word diet. And we try to keep our variables as short names, acronyms, no more than 1 or 2 words, if at all possible. But so the I and the C by default are two different treatment groups or conditions within an independent variable. And here we have an independent variable diet, and it has these two different groups, one getting the keto and one getting the regular. So imagine just basically what's happened. Imagine we've invited a whole group of patients to a meeting room, and there we flip a coin, and if it's heads, they go to one group, if it's tails, they go to the other group. And so now we're going to give them both this diet, we're going to send them on their way, and we'll come back in 6 months and see who has the greater weight loss. That is what this question is kind of alerting us to as the design for this study. The O in the PICO by default is always our dependent variable. In this case, it would be weight loss. So we'll have one group on the keto diet, we'll see how much weight they lose. We'll have the other group on a regular diet, see how much weight they lose, and we'll compare those two weights. Actually, we'll take the average, the mean weight loss of each group, and compare that to see if one of these diets is significantly different than the other. We might find that the patients on the keto diet lose significantly more weight than those on the regular diet, as an example of an outcome of such a study. But the PICO is really meant to be a training tool. We write out our PICO, just as I gave you an example here. But if we were going to actually write this in a formal paper, we might streamline it. So you often, or perhaps seldom, will not see this. You often see the question reduced to something simpler, and it might not have the element of time with it. Somewhere else in the write-up of the article or the research study, you'll find out that the time period was over 6 months, but it may not appear actually in the question. So this type of question, when we have a PICO, can only be answered with a comparative statistical test, and that's because really we're comparing these two groups with one word, greater. For example, we have two variables here. We have diet, we have weight loss, so this can't be a descriptive study. We don't see the words associated with or association, correlated with or correlation, related to or relationship, so it can't be a correlation. We don't see the word prediction here, so it's not an epidemiology, it's not a regression question, and we don't see anything in terms of risk or likelihood or some kind of rate that would maybe push it into our epidemiology group. This kind of question, a PICO question, can only be answered with one of our comparative statistical test group. And I like to divide all of these tests up into two major groups. One is what I call a t-test track, and their non-parametric equivalents, and the other will be the ANOVAs and their non-parametric equivalents. Chi-square and its derivatives actually fits into both, so we'll mention that with both of these. In this part 2, we're going to look at the t-test group, and then we'll come back at part 3 and look at the ANOVAs. In statistical textbooks, in statistical classes, you will often see all of these tests mentioned as being one of several different groups based on the way they work. I throw them all in the comparative statistical test group because they all answer that question about, is there a difference? It might be expressed as an increase or decrease, but all of these tests only answer that one question, is there some difference that we're seeing in our research study? The comparative statistical test group is of much greater strength than the correlation group. This is the level of tests that we can use if we have lots of information at this level. This is the kind of information we need to go out and make an evidence-based practice change. So the t-tests. We have 3 different t-tests, and they all do basically the same thing. They compare the means between two groups to see if there is a significant difference that could not have occurred just by chance. So let's look at the 3 different t-tests. The independent samples t-test compares 2 completely different groups. For example, in the prior question we asked, we have 2 groups. One's getting the keto diet, one's getting the regular diet. Nobody can be in both groups. We go out, we study them, we see if there's a difference. Independent groups, independent samples t-test. The paired samples t-test is a little bit different. This is when we have a pre and a post-test situation. So imagine we have all of our patients in a clinic. Everybody's been on the regular diet. We've been trying to get them to lose weight. They want to lose weight. We track them for 6 months on the regular diet, and we know how much weight they've lost. We have an average weight loss for our group. Then we find out, and we've been struggling, for example, trying to help these patients lose weight. They want to lose weight. We want to help them lose weight. And we discover something called the keto diet. So we decide we'll try to get everybody in this group to go on the keto diet. So some participate, some don't. Those that don't want to participate, they're not required to. I'm just painting an example of a scenario that might occur. So now we have this group of, say, 75 patients that were on our services. We've been following them for 6 months. They've been on the regular diet. Now we're going to put all of them on the keto diet. They've all agreed to participate in the study. This is a pre-test, post-test. The pre-test was the regular diet. Post-test is the keto diet. And now we're going to compare these 2 different treatments to see if there's a difference in weight loss. Same group of patients. Everybody in this study is getting the exact same treatment. They were on the regular diet. Now they're all going to be on the keto diet. This is when we use the paired samples t-test. It's called paired samples because each of our participants will have 2 numbers. Our first participant was Bob. We found that he lost 12 pounds in the first 6 months on the regular diet, so he's got a 12 for the first part of the study. Now in the keto diet for 6 months, he loses 20 pounds. So we have 2 numbers, paired data, for each of our participants like Bob. We have the pounds lost in the regular diet and the pounds in the keto diet, and we can compare the two. We're still comparing the means of two groups, essentially. We're comparing the pre-group, even though it's the same patients, same participants, we're measuring the mean of the pre-group with the post-group. A third type of t-test is an interesting test. It's called the single samples t-test. It's when we have a mean of our group and we're comparing it to some national mean. We have a large BSN class. They went out and took maybe the national NCLEX some prep test. We know that their average score was 90, and we look into the data and we find out that the national average on this prep test is an 85. And so now we're comparing our 90, the mean of our group, to some national mean. We do this a lot in healthcare where we have some national benchmark number that we're trying to see if our group of patients can meet. So anytime you see that, you might think of that with the single samples t-test. It's often used when we're comparing the mean of our group to some national or known mean. Notice in all of these three t-tests, the independent samples t-test, paired samples t-test, and the single sample t-test, we're only doing one thing. We're comparing the means of two groups. And in order to have a mean, we have to have scale data. So if we don't have scale data, for weight loss, we just said, well, this person had very little weight loss. This other person had a moderate amount of weight loss. The third person had significant weight loss. That would be ordinal data. If we have ordinal data, we cannot use any of these t-tests. Again, all the t-tests can do is compare the means of two groups. And to do that, our data has to be measured at the scale level. Overall, in considering the three, probably the paired samples t-test, if you wanted to know, is a little bit stronger. And that's because in the example I gave, if you think about it, we have a group of patients. We had 75 patients. They were on the regular diet. And now those same 75 patients are going to go and try out the keto diet. We really eliminate a lot of variation by having that same group. Now, granted, there is the element of time. It might be that in the first 6 months, the regular diet, it was right before the pandemic started, and we decided to continue our study through the pandemic, and that might have affected the amount of weight loss. It might be that there's a war. It might be that the economy's in recession. It might be that we had a major hurricane come through, but we decided to continue with the study. Those variables probably will impact our results. But other than that, having that same group in the pre and post test is stronger than in our first example where we had patients come in. We divided them at random into a keto group and the other half into the regular diet group. There might be some variations in those patients that would impact the results of our study. That's why I would consider the paired samples t-test a little bit stronger. But there are often times that we can't use a paired samples t-test. And this is an example. We have a hospital, we have a medical surgical unit, and we've been noticing that our patients have had falls. Our fall frequency is higher than that of than our national average. And but we want to study something. We want to implement a new rounding method, for example, where we're going to make sure that we see every patient very frequently to make sure they're not trying to get out of bed where they could get into trouble and fall. And if we're counting falls, it might very well be that we have one group on the unit in the past, and now we've implemented something new for every other new patient, and now we just can't have this pre-test, post-test design. We have to use the people that were on the unit in the past and compare them to the people that are on the unit now. And that's why we get into situations where we have two completely different groups that we have to use the independent samples t-test. They're both very good. I would just say that if you can use the paired samples t-test, if you can do a pre-post test design, it is stronger than having two completely different groups. So I said that the t-test can only compare means. It is often the case that we have ordinal data when we're measuring a dependent variable. When we have ordinal data in our dependent variable and can't use the independent samples t-test, we use its non-parametric equivalent, the Mann-Whitney U. And if it's nominal data, we'll use a test called chi-square that I'll come back to in a few minutes. Sometimes chi-square can't be used, and we use an alternative type of chi-square called the Fisher's exact test. In the case of the paired samples t-test, if we don't have scale data, if we have ordinal data, we can use the Wilcoxon sign rank test. And if we have nominal data, we can still use the chi-square, only in that particular case where we have paired data being compared. It's called the McNemar, which is a version of chi-square. If we are comparing rates, this is a test that I put in the epidemiology group, and I'll show you an example of that. When we have a comparison of rates, we use what's known as a z-score for two population proportions. So in total, we've covered 10 tests in this t-test track. So think about this. We started off with a question, a comparison question. It sent us to the comparative group. In that comparative group, we found out we had one independent variable with two different conditions. This led us into the t-test track. Then we found out if we were comparing our data to maybe a national norm, if it was a pre-test, post-test, or if it was two independent groups. That led us to our three t-tests. And then we look at the level of data. If the level of data was scale, we could use a t-test. If it was ordinal, we had to go with its non-parametric equivalent. And if it was nominal, we went with chi-square. That's why it's very important to be able to identify the level of data being used. Just as a little bit of a sidebar, over the years I've worked with over 1,000 DNP students on their final capstone projects, all of which were basically evidence-based projects, where they were implementing a new procedure that they thought would improve an outcome over the way things had been done. And so basically they all started off with a PICO question, almost all of them. Of these 1,000, just to show you, about 25% of them wound up using chi-square, 20% had a paired samples t-test, another 20% used the independent samples t-test, 10% about used the Mann-Whitney U, 5% the Wilcox sign rank test, 5% McNemar. A few of them used the z-score for two population proportions. They were comparing an infection rate before and after some new implementation. In probably about 10% of the cases, the sample size was so small, something less than 24 participants, that they wound up using descriptive statistics. And I mention this because what happens is, if we have a very small group, think about our diet. We have half of them going into the keto diet, half of them going with the regular diet. We think we can use an independent samples t-test. But when we get very small numbers, if we have, for example, 12 on the keto diet, 12 on the regular diet, that number is going to be so small that the t-test just simply won't work. We don't have enough participants to have a really good solid mean, a good feel of what's going on with that, in this case, diet or treatment group. And what happened with those students was their sample size was so small that all these tests just start to fall apart at that point. So they use descriptive statistics. And in that case, you might say of the keto diet, the average weight loss was 3 pounds. Regular diet, the average weight loss was 1.5 pounds. And you could write up your results like that and just let the numbers speak for themselves. You won't be able to find out if one is more significant than the other. 2% of the other, or some of the students actually did not use a PICO question. They were doing something kind of completely different. In some cases, they were comparing 3 treatments at one time, and that led them to using an ANOVA. And as we saw in the PICO, you really only have 2 treatment groups. You have the I group and the C group. There's no third group in the PICO. So those students used basically a one-way ANOVA, which we'll get to in another part of this class. So the independent group, the independent samples t-test is used to compare 2 independent groups, determine if there's a difference. We talked about the PICO question, so you have another example of that here. And you can follow this scenario and see how that looks to you. Before concluding the t-test, I want to go over just briefly the kind of information we get from a statistical package known as SPSS. This is the output we get, and I know it looks like a lot of numbers, and I know it's very small. I just want to point out what's absolutely the most important information here. In this study, we had two groups being compared. Please disregard age and gender. If you want to, you can think of this as being something like two different diets, something like that were being compared. There were two different conditions, 1 and 2. For condition 1, we had a mean of 66.308, and for the second condition, we had a mean of 67.808. So SPSS actually figures out our mean for us. We don't need to calculate this. In another video, I'll show you how to run these if you want to see those, but this is the kind of output we get. So the first thing here, the most important thing here, is we get a mean for our two groups. And as you can see, this isn't very different, right? If we had a mean of 66 and now we have a mean of 69, if we round that off, it's not really a whole lot of difference. So this is what the independent samples t-test results look like. And in another class, we talked about the importance of doing two-tailed tests. SIG is short for significance or p-value. So here we see with equal variances assumed that we have a p of 0.621, which is high. So here we would fail to reject the null. We'd say that these two groups are not statistically significantly different. We also get our confidence interval over here. I mentioned this because in another class I talked about this, that we don't actually have to figure that out, that SPSS will do that for us. And remember, the confidence interval is an estimation of the mean of the population. We only got the mean of the sample here. This is a mean estimate for the population. Paired samples t-test SPSS output looks very similar. Here we have a pre and a post pairing. In our pre, our mean was 3.33. I ran this data. I honestly don't remember what this was, but we're comparing, I think, satisfaction before some intervention and then satisfaction after that intervention. And we got a 3.3 before and a 7.0 after. You will get a correlation. That's not really part of the paired samples t-test. It's just something that SPSS gives us. So here we can see our paired samples t-test results, where we have a significant difference of a p of 0.014. So in this case, because it's below 0.05, we could reject our null and say we did have a significant difference. Lastly, when we run a chi-square, we get a couple of things that are interesting points of information. The first is, in this case, we were asking patients with two different types of disease, we'll just call them 1 and 2, how satisfied they were with their care. And for satisfaction, all we had was 1, yes, is satisfied, and 2 meant no, not satisfied. So if you look at the people with disease 1, out of 31 patients with that disease, 17 were satisfied, 14 were not. And those with the second disease, whatever that diagnosis was, of the 47 who had that disease, 23 were satisfied and 24 were not satisfied. And this is the kind of comparison that we can get with a chi-square test, where we see if there's a difference in the frequency of these two nominal events of being satisfied and not satisfied. So this is called a cross tabulation, where we get these cells, as they're called, and we can look at this and kind of see how our data came out. By the way, again, we would enter the data in SPSS, press a few buttons, and SPSS gives us this information. SPSS will also give us our significance or p-value. The one that we report in this case is we can report the Fisher's exact test. That would be used if the cell sizes were low. We really like to use the Pearson chi-square test results. And here we would have a p of 0.610, and we would basically say that there's really no statistical significant difference in satisfaction between those with disease 1 and disease 2 because our p is 0.610. These other things that SPSS gives us are different types of chi-square tests, but by convention, almost all of the time, we'll use the Pearson's chi-square. We will use the Fisher's exact test if we have low numbers in these cells that would make our chi-square not work for us. So that's the kind of information we get from SPSS for a chi-square. And this concludes part 2 of our discussion on our comparative test group.